Hi, welcome to this new MATLAB series. I'm Alberto and I am one of the two MATLAB ambassadors here at Politecnico Milan. Today we are going to show you, and in the future release, the MATLAB and ROS series. In particular, with this series we're going to speak about the hardware setup and connection between MATLAB and a robot, the kinematic and odometry using MATLAB for a mobile robot, the local planner, the mapping, so understanding what are the environment in which the mobile robot is, and the global planner in order to develop tasks for this robot. Today, the agenda for today will be ROS introduction, so what is ROS and how it became so important in the robot industries. The hardware setup that we're going to use in the future videos and how we develop it. The ROS setup, so how to install, configure ROS. And last one, the connection, so how to connect MATLAB and ROS. So let's start with ROS. What is ROS? ROS, it means Robotic Operating System. And it's in particular is a middleware, so it stays a little bit above the operating system. And the main purpose of ROS is the capabilities of interact between the software and the hardware. Okay. It's very used and it's based on Python and C++, so has a variety of nodes, and it's very supported by the standards, and it contains also a packing and building system. So when you write a particular code, you can build it inside the environment, the ROS environment, and it has a vibrant community, so it means that lots of people work with ROS and develop softwares. So the why we want to use ROS is mainly because it's very popular in academic and commercial research, such as you can see in this graph. So currently we have around 16 million downloads and lots of papers and research that use ROS. So there's a big community that use this software in order to develop new things. And also this is very important because ROS gives the opportunity to integrate and seamlessly move through simulation to hardware. So this is the capabilities to use the so-called model-based design. Okay, so we can use simulation in order to develop something and then deploy it on the hardware. But let's see in particular where ROS is used. ROS is used in a variety of continents. In fact, first it's used by mobile robots such as cleaning, security, and small robots. But staying with the wheels, it's used also on vehicles and on, let's say, military or any type of moving vehicles. But also it's used in the industry of the industrial robotics. So let's say the robotic arms, the medical surgical robots, lots of things. But also nowadays with the rising of UAVs, it's used also on to the let's say drones, so into the flying robots. Okay, all these type of context are using ROS. Okay, so let's say that it's very, very important to understand how ROS works and how we can use with MATLAB. Okay, ROS it's based on the distributed system. It means that there's different players inside ROS, and these players are called nodes. So we have the node A that does some type of things. It's a software, and there's the node B that is another software that does other things. These two, let's say, islands need to communicate. In order to communicate, they use the so-called topic. Topic is a particular way to exchange messages. In fact, the node A wants to communicate something to the node B, so it publishes something on a topic, on let's say a message, and then the node B subscribe to this message. So say, okay, node A say it's 10 o'clock. Node B want to know what is the hour, subscribe to the same topics and read the information, so it's 10 a.m. Okay, perfect. What are the workflow from the idea to the production. Usually, we will have to build the requirements, so formalize what is the idea, then design something, read the code in C++ or Python for ROS, then implement it onto the hardware and then put it on production. But now with MATLAB, we can have the idea, build the requirement, use MATLAB and Simulink to seamlessly integrate the idea and the design. So we can develop a simulator, we can work with all the tools that we need and we know. And then when we have done the first part, so the designing and the simulation, we can use the robotic toolbox. So the toolbox that allow the MATLAB and Simulink software to be compiled for ROS, and then use ROS for the implementation. And this is very helpful and faster because allows us to use all our knowledge about MATLAB to develop very cool things on the production. Okay, so as I said before, we can use the so-called model-based design. So the classical V-shape. So we explore the ROS internet network. So we know what are the capabilities of our robot. We can develop the algorithm. So we can understand what is the algorithm. We can write the code and blah, 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 blah. We can do some simulations. So test the algorithm on the computer. Then deploy it onto the ROS robot. So compute the software and put it alone on the robot, then test it on the real hardware, on the real robot, do some performance analysis, and if it's all good, we can put it in production and say goodbye to our robot that will change the world. Okay. And this is the introduction of ROS. So now let's move to the hardware setup, because we need to know what is the robot that we build and we're gonna use for this series. Okay, we decide to use a robot that is a moving robot. So we need some wheels, a body. Then to move this wheel, we need the motors. And in order to use this motor, we need some motor drivers. So something that give the power to the motor. And this is the actuator part. Then in order to know what the robot is doing and what is the different and the ambient, the environment in which is the robot, we need the coders on the wheel, so that measure how long and how far the robot moves, and also the LiDAR, that is a specific, interesting hardware that measure distances. I will treat these different, let's say, components one each other. Okay, so we built this, and this is the assembled robot. So it's a robot in the real world that is able to move, it's able to acquire information, and it's able to run ROS in particular. Okay, so it's built using the motors and the wheels and some easy and cheap parts such as wood plywood. Then it's used as actuator the motor. So there's a battery that provides energy to a controller, a driver for the motor, and then the motor to generate the motion in order to move the robot. Then, in order to acquire information, we are going to use encoders that are a specific hardware to read and know exactly how long and how the wheels are moving. So it's measure the angle of the wheel, and also a LiDAR. The LiDAR is a particular hardware that acquires distance from the objects using a ladder, and in particular it can build maps, and as you can see in the picture, know exactly the distance of each point from the center of the laser. Speaking about the brain of this robot is Raspberry Pi. Raspberry Pi is an embedded computer that is very used in the maker community, and it's fully supported by MathWorks and has some support package for MATLAB. And we're gonna see later how to set up this and how to implement the different things. But now let's see in the real world how this robot is built. So let's move to the demo.
So welcome, this is the demo. Okay, so I just explained to you that the robot is composed by the wood frame here, okay, on which is attached this, that is the motors and the track of a skateboard, and these wheels provide the motion to the overall systems. In particular, the motor spins. There's a belt inside here that transmits the motion to the wheels. Okay, and this is the actuation part. In fact, here under the robot there's the batteries, so the power generator, the batteries that gives the power to the inverter. This is the driver of the motor. Here give the source, there's the output, and these inverter are connected through USB cables, okay, here to the Raspberry Pi. Raspberry Pi that is inside this case. Okay, you can see there's the 4 USB ports and the Ethernet connection. Okay, the Ethernet connection is connected to this router. The router provides the connection to the MATLAB computer. Here in the front part, there's this. Under the white cover, there's the encoder. The encoder reads the turn of the motors, and it provides the information about how long and how the motor is turning. So it measures the turning of the motor, and it gives us the information about the speeds of rotation. Okay, here on the top part there's the LiDAR. This LiDAR is a let's say it's rotating very fast. Okay, and rotating very fast, it's there's one hole that output the laser, and the other hole that measure how long it takes to bounce back to the motor. Okay, now I can switch it on so I can show you how it works. Okay, there's the LiDAR that is running. Perfect. The motor now are connected, and it function. Okay, also there's some add-on, but they are not the key point here. There's a camera for acquiring image. There's a speaker in order to say sentence and to communicate with the user, and there's the handlebar. This is only for transportation. You can pick it up from here. Okay, I hope you enjoy this demonstration. Let's go back to the presentation.
Now, back on the presentation, we're gonna see about how to set up ROS. ROS is can be set up on the Raspberry Pi Model B using this SD card, a charger, and an Ethernet cable. We need to go on the add-on, then we can select the specific add-on for Raspberry, and then download it. Once we download it, it's the let's say the specific software to set up the Raspberry. So we can set up later. In order to set up later, we need to do it on a manage, then click on the gear, and then follow these instructions. So select the correct hardware. In particular, our case is Model 3B+. Okay, next we can select that we want to flash a fresh new Raspbian image. Okay, download it. Then we can select it from our download folder, the zip file. We can select it. Okay, we can validate it, and we can say how we can connect to the Raspberry, because it has different ports and connections. So we decide to connect it through LAN, through wireless, or connected directly to the computer. we decide to connect it through the network. We need to specify the Wi-Fi ID and password, okay, and then we can select automatically the IP of the Raspberry, so it does our research on our local network and find the Raspberry. We need to flash the software on the SD card, so we put inside the computer. We can select the right, let's say the right SD card, and then flash it on the SD card. Then we can insert the card into the Raspberry Pi. Switch on the Raspberry Pi and wait some seconds. When we are sure that the Raspberry Pi is booted, the computer research it, and then we can do the test of the connection. It means that we can be sure that the Raspberry Pi has been installed correctly, the OS and the ROS is installed correctly, and then connect it through with the computer. Of course, there's different ways in order to do this, depending on how is your configuration of the PC and the Raspberry. Okay, once we have done this, we can finish and we are sure that for the connection. So we have now installed Raspbian, ROS, and we are ready for the, let's say, to work with the Raspberry Pi. On the other hand, on our PC, we have installed MATLAB on one of our operating systems. So it's not important if you're using Windows, MATLAB, or Mac or Linux, because this works with all the platforms. Okay, so now we have understood how to install ROS on the Raspberry, and we have ready the computer. We need now to build and to put the different blocks that now here are in green in order to communicate to the actuator and read from the sensors. Let's see more in depth how this software is set up. In particular, from the bottom, we have Raspbian that manage the OS and the hardware interface, so the drivers. Okay. Then we have ROS. Stuck on them, there's the master, so the head of the different nodes, and then we have the 4 nodes that are in charge of the communication. Okay, so starting from the left, we have the motor. The motor needs some commands, and these commands are provided by the hardware. In order to set this command, the left motor node subscribe to the right command's speed. Okay, so it means that there's a topic called right command speeds that contains the velocity in RPM. This velocity is then taken from the left motor node and give it to the left motor. Okay, the same for the right motor. For the LiDAR is the opposite, so the LiDAR provide information to the LiDAR node. The LiDAR node write on the /scan topic, and so it publish something on this topic. Then there's some other players inside the environment, such as MATLAB, for example, want to know the LiDAR information, will read this information. The same for the odometry. So the encoder will generate some information inside the odom node. This node will publish something on the left speed topic and into the right speed topic. And this became the, let's say, the what we are gonna see later in the MATLAB, because once we have set up it properly and correctly, we can forget how it's been developed and built, because we can only interact with this topic. Okay. So for the last part, we can speak about the connection. And in order to speak about connection, we will literally move to MATLAB and see it in the real world. So let's go on to the MATLAB environment. So here we are on MATLAB. We have to specify very few commands in order to connect to the robot. Firstly, we have to write down the IP of the robot, in this case the local IP. Second, we have to use the command rosinit. Rosinit is a very smart command because it contains different options. If you type down only rosinit, you will create a ROS network on your PC. If you, such as in this case, write down rosinit and then the IP of the robot, you will connect to the robot and use the local ROS network inside the robot. So now MATLAB is connected to the robot, and all the things we are gonna see, the topics and the other software, can be run both on the robot or on MATLAB. In this case, we have just connected. And you also don't need to specify your IP because it's already known by the system, and it's right down here. Okay. Now we can do the command ROS topic list. Is the usual command to see what are the topics that are now running on the robot. And as we can see here, we have lots of options, such as the information about the speeds, so the encoders, the information about the LiDAR, so the scan topic, and then the possibility to command the speed of the left motor and the right motor, such as the one that we have just explained. Now, how we can connect Simulink to the robot? Firstly, let's open Simulink. Then open a blank model. Okay, here we are. First, we need to go to Apps and then select Robot Operating Systems. Of course, this is a package, you must download it and install before using it. Then you have to select the right ROS type, in this case ROS1, ROS, and click Finish. Now Simulink sets itself to be connected to that type of network. Then we must click Connect to Robot, specify the IP of the robot, the username, the password, the type of ROS installed, in this case the kinetic version. You can find it on the ROS site, or you can discover more on the MathWorks site. And then you have to specify Catkin workspace. The Catkin workspace is the same as the workspace of MATLAB, so it's a kind of place where all the code will be compiled and stored. Meanwhile, the execution, so in this case it's called zig_ws workspace, and then I can click Test. Test open up this configuration panel and diagnostic panel that says, okay, ping the robot successfully, then establish the connection with the SSH protocol, then testing the privilege and so on. Now we are sure that the robot is discoverable and we can connect to it. So once we have done test, we can click OK. Perfect. Now here, what we're gonna do here, it's the ROS node that we can use to develop whatever we want. In particular, in the following series, you will see how to fill up this blank space. So now let's go back to the presentation for the last few information. Okay, I hope this is clear for today. I encourage you, if you have questions, to reach us from the Facebook or Instagram community that you can find here on the right, and don't forget to subscribe and leave a thumb up if you like this video, and don't forget to see the other videos of this channel, because I think they can be very helpful for you to better understand the capabilities and the opportunity that MathWorks give us as students. Okay, bye bye, see you next time.